Galaxies are the fundamental luminous building blocks of the cosmos, vast, gravitationally bound systems of stars, gas, dust, and dark matter, spanning a range almost too large to picture. The faintest dwarfs contain only a few million stars. The most massive giant ellipticals hold more than 1 trillion. Between those extremes lies a bewildering variety of forms: smooth spheroids, majestic spirals, chaotic irregulars, and the central task of this chapter is to make sense of that variety. We will build the framework by which astronomers classify galaxies, beginning with Edwin Hubble's famous tuning fork sequence, then dissect the components from which every galaxy is assembled: bulges, disks, bars, and halos, examine the physics of spiral arms and the hidden order within elliptical galaxies, and finally turn to the remarkable scaling relations that reveal galaxies, for all their diversity, to be a single, physically ordered family, governed by a few deep and reproducible laws. The very recognition that galaxies exist beyond our own dates only to the 1920s. For centuries, the faint spiral smudges catalogued by astronomers were of uncertain nature. Were they nearby clouds of gas within the Milky Way, or distant island, universes of stars in their own right? The question was settled in 1925, when Edwin Hubble identified individual Cepheid variable stars in the Andromeda Nebula and used them to measure its distance. Andromeda lay far beyond the bounds of our galaxy, a separate stellar system of comparable grandeur, and the long debate over the scale of the universe was resolved at a stroke. The cosmos, it turned out, was populated by galaxies without number, and they span an enormous range. The faintest dwarf spheroidals hold only a few 100,000 stars, while the giant galaxies at the hearts of great clusters exceed 1 trillion solar masses in stars alone, a span of more than 6 orders of magnitude in mass. Why classify galaxies at all? Because morphology is not mere description. A galaxy's appearance correlates strongly with its physical nature: the age of its stars, its gas content, its rate of star formation, its motions, even its cosmic environment. Its form is a diagnostic of its history. When the Galaxy Zoo project enlisted hundreds of thousands of volunteers to classify 1 million galaxies by eye, their verdicts agreed with professional astronomers to within a few percent, and cleanly separated the population into disk-dominated, star-forming systems and spheroid-dominated, quiescent ones. Yet one caveat frames the whole subject: morphology depends on how you look. The same galaxy appears as a knotty, blue, clumpy disk in ultraviolet light, tracing its young stars, and as a smooth red ellipse in the infrared, tracing its old stellar mass. Classification schemes are human constructs imposed on a continuum, but they endure because they encode real, reproducible physical distinctions. The foundational scheme is the Hubble sequence, which Edwin Hubble introduced in 1926 and immortalized in his 1936 book The Realm of the Nebulae as the iconic tuning fork diagram. At the handle sit the smooth, featureless elliptical galaxies. The handle then splits into 2 prongs: ordinary, unbarred spirals along the upper and barred spirals along the lower, with the transitional lenticular galaxies at the junction where the fork divides. Hubble labeled the ellipticals early type and the spirals and irregulars late type, a terminology that survives to this day, though it carries no implication about evolutionary age. Hubble did not intend his sequence as an evolutionary track, and galaxies do not, in general, slide along it from elliptical to spiral over their lifetimes. The words early and late are simply convenient shorthand, and the sequence itself remains, a century on, the universal language of galaxy morphology. Consider first the ellipticals, the smooth spheroids at the handle of the fork. They are denoted by the letter E and a number from 0 to 7, encoding how flattened they appear. The figure is 10 times 1, minus the ratio of the minor to the major axis. An E0 galaxy looks perfectly circular. An E7 is the most flattened elliptical ever seen, and non-flatter exists, a limit later understood through the dynamics of systems held up by random stellar motions rather than rotation. A crucial subtlety is that this flattening is only apparent, a projection onto the plane of the sky. A truly spherical galaxy and a flattened, cigar-shaped one seen end on both present the same circular outline. The observed shape of an elliptical is thus an ambiguous clue to its real 3-dimensional form, a puzzle resolved only decades later, by measuring how the stars within them actually move. The spirals are subdivided into types SA, SB, and SC with barred counterparts, by 3 criteria that change together along the sequence. First, the prominence of the central bulge, which shrinks from the large, dominant bulge of an ESA to the almost negligible one of an SC. Second, the tightness of the arms. An SAs are wound tight around the center, while an SCs open into loose, sweeping curves. Third, how far the arms break into individual knots of star formation, glowing clouds of ionized hydrogen, clusters of hot young stars, and dark lanes of dust, which increases toward SC. Between the ellipticals and the spirals sit the lenticulars, a lens-shaped class Hubble proposed almost hypothetically. Galaxies with a prominent bulge and smooth disk, but no spiral arms and little cool gas. Anything fitting none of these regular forms is simply classed irregular. Hubble's scheme was extended and quantified from 1959 by Gerard de Vaucouleurs, whose revision remains the modern standard for classification by eye. He replaced Hubble's discrete boxes with a continuous numerical stage, running from strongly negative values for ellipticals through 0 at the lenticular to spiral transition to strongly positive values for the latest types, extending the sequence beyond SC to the ragged SD and on to the Magellanic types, disordered and almost bulgeless. He added a richer notation to record whether a galaxy is barred, unbarred, or intermediate, and whether its arms spring from an inner ring or thread directly to the center. On this system, the Milky Way is a barred spiral with an inner ring and arms between the SB and SC classes. Modern surveys go further still, replacing the human eye with quantitative measures of concentration, asymmetry, and clumpiness, and with machine learning classifiers trained on millions of galaxy zoo labels. Beneath these labels, every galaxy is assembled from a small set of recurring components. The first is the bulge, the central, three-dimensional swelling of stars at the heart of a disk galaxy, and modern work recognizes two distinct kinds. Classical bulges resemble miniature ellipticals embedded in a disk. Held up by the random motions of old, metal-rich stars, they are thought to form rapidly, through early mergers and the dissipative collapse of gas. Pseudo-bulges, by contrast, are built slowly and gently from the disk itself, as bars and spiral arms funnel gas inward over billions of years. They rotate like the disk, are more flattened, and often show ongoing star formation and delicate inner spirals. A third variety, the boxy or peanut-shaped bulge seen in some edge-on galaxies, is not a true spheroid at all, but the inner part of a bar that has buckled and thickened out of the galaxy's plane. The second great component is the disk, the flattened, rotating sheet of stars and gas in which nearly all of a spiral star formation occurs. Its brightness falls off in a characteristic way, dropping smoothly and exponentially from a bright center toward a faint edge, with a scale length that measures how far the light reaches. Most disks are in fact double, a thin disk, only a few hundred parsecs deep, holding stars of all ages on nearly circular orbits, and a thicker disk perhaps 3 times as deep of older, more metal-poor stars on hotter paths, a fossil of the galaxy's turbulent youth. Threading through the center of roughly 2/3 of all disks is the third component, the bar. A straight stellar structure that acts as a dynamical engine, redistributing angular momentum, driving gas inward to fuel star formation, and slowly building the pseudobulge from the material it delivers. Surrounding the visible galaxy are 2 further components, one barely luminous and one wholly invisible. The stellar halo is a diffuse, roughly spherical cloud of the oldest, most metal-poor stars, together with the compact swarms of globular clusters, of which the Milky Way holds around 150. It contains only a few % of a galaxy's stars, but it is a precious archive. Its stars and clusters are the shredded remains of smaller galaxies swallowed long ago. Enclosing everything is the dark matter halo, the dominant mass of all, an extended, roughly spherical distribution, inferred from the flat rotation curves of disks and the motions of satellites. For the Milky Way it exceeds 1 trillion solar masses, dwarfing the 50 or 60 billion locked in its stars. The luminous galaxy, in truth, is a bright ornament at the center of a vast dark cloud. To make morphology quantitative, astronomers model how a galaxy's surface brightness, its light per unit area on the sky, falls with distance from the center. The unifying description is the Sersic profile, introduced by the astronomer José Luis Sersic in 1968, which captures the whole range of galaxy light with a single adjustable number, the Sersic index. When that index equals 1, the profile is a simple exponential, the law obeyed by the disks of spirals. When it equals 4, it becomes the steep, centrally concentrated profile that de Vaucouleurs had found in 1948 to fit elliptical galaxies beautifully. Real galaxies span the range and beyond. Low-mass ellipticals sit near 1 or 2, while giant ellipticals climb to 6 or 10, their light spread into vast, faint outer envelopes. The index thus becomes a continuous, measurable stand-in for morphology, and by fitting a bulge and disk together, astronomers recover the bulge-to-total light ratio that quantifies Hubble's original criterion. Return now to the ellipticals, for detailed study has overturned the old view of them as simple, dynamically dead spheroids. When they are isophotes, the contours of equal brightness are carefully fitted with ellipses. The tiny residuals betray a hidden structure. In some, the contours bulge outward along the major axis, revealing a faint embedded disk. These are disky. In others, the contours are squared off toward a rectangular, boxy shape. This distinction, measured from the subtle harmonics of the isophotes, is no cosmetic detail. It sorts the ellipticals into two families that differ in almost every other property: in mass, in the structure of their cores, in the chemistry of their stars, and most tellingly, in the way their stars move. What looks like a single smooth class of object is in fact two, distinguished by the faint fingerprints written into the shapes of their outer contours. Integral field surveys such as Atlas 3D, which map the motions of stars across a galaxy's whole face, revealed what that division means. The disky ellipticals are the lower mass, fast rotators. Much of their support against gravity comes from ordered rotation. They have steep, cusped centers, and they form a continuous family with the lenticulars and the bulges of spirals. The boxy ellipticals are the slow rotators, the most massive galaxies in the universe which barely rotate at all, held up instead by the disordered motions of their stars. They show scoured-out cores, where a pair of merging supermassive black holes is thought to have flung stars away, and their chemistry records a rapid, early burst of formation. These contrasts point to divergent histories: fast rotators built through gas-rich mergers that preserve spin, and slow rotators assembled by repeated gas-spore collisions that erase it, the giants that crown the centers of clusters. The most beautiful feature of a spiral galaxy is also the source of a deep puzzle. A galactic disk does not turn as a rigid body, it rotates differentially, the inner regions completing an orbit far sooner than the outer. If the spiral arms were simply fixed lanes of the same stars, this differential rotation would wind them ever tighter, wrapping them into an unrecognizable coil within a few galactic turns, a small fraction of a galaxy's age. Yet open, well-defined spirals are everywhere we look, and they are plainly not a fleeting phase. This is the famous winding problem, and its resolution forced astronomers to abandon the natural assumption that a spiral arm is a material object. The arms cannot be permanent assemblies of particular stars, dragged around with the disk. They must be something subtler, a pattern that outlives the matter passing through it. The leading resolution is density wave theory, proposed by the astronomers Lin and Xu in 1964. In their picture, the spiral arms are not fixed groups of stars, but a quasi-stationary wave, a travelling zone of enhanced density that rotates rigidly, at its own single pattern speed, quite distinct from the orbital speed of the stars and gas streaming through it. Stars catch up to the wave crest from behind, slow down and pile up within it much as cars bunch together at a slow patch on a motorway, and then pass out the far side and speed away. Because it is the pattern that persists and not any particular matter, the arms escape the winding problem entirely. The radius at which material and pattern happen to move together is the corrotation radius. Inside it the stars overtake the arms, and outside it the arms overtake the stars. Density wave theory also explains why the arms shine. As gas orbits into the crest of the wave, it is abruptly compressed, and the shock triggers the collapse of giant molecular clouds into new stars. That is why the arms are picked out so vividly by glowing clouds of ionized hydrogen, by clusters of hot, short-lived blue stars, and by dark lanes of dust. They are assembly lines of star formation, lit by the very stars they forge, yet not all spirals are so orderly. Only about 1 in 10 are the classic grand design spirals, with two bold, symmetric arms sweeping right around the disk. The whirlpool is the archetype, its pattern reinforced by the tug of a passing companion. Others are flocculent, their arms broken into patchy, woolly fragments, born not of a coherent wave, but of star formation sheared into arcs by the disk's own rotation. Beyond the regular spirals and ellipticals lies a vast population the tidy Hubble sequence describes only crudely. For by sheer number, the universe is overwhelmingly made of small, faint, irregular galaxies. These have no organized spiral or ellipsoidal form. They are typically low in mass, rich in gas, poor in heavy elements, and busy with patchy, vigorous star formation. Astronomers distinguish the Magellanic irregulars, disordered but showing a hint of rotation or a bar, from the genuinely chaotic systems whose disorder betrays a recent collision. The nearest and best studied are the Milky Way's own companions, the large and small Magellanic Clouds, blue, gas-rich, actively star-forming satellites some 50 to 60,000 parsecs away, with far less than the Sun's share of heavy elements. Their ragged appearance is partly intrinsic and partly the work of tides, as the Milky Way and the two clouds gravitationally stir one another. Fainter still are the dwarf galaxies, conventionally those below about 1 billion solar masses, and they come in several kinds. Dwarf irregulars are gas-rich, rotating, star-forming little disks. Dwarf ellipticals are smooth, gas-poor spheroids and the single most numerous type of galaxy in nearby groups and clusters. Faintest of all are the dwarf spheroidals, gas-free, ancient, and so diffuse as to be nearly invisible, yet so dominated by dark matter that their stars move as if embedded in halos hundreds or thousands of times more massive than their light suggests, making them the most extreme dark matter laboratories known, the ultra-faint members holding fewer stars than a modest star cluster. In the local group, the gas-rich dwarfs lie in the outskirts, while the gas-poor ones huddle close to the giant galaxies, a trend betraying how infalling dwarfs are stripped and transformed by their massive hosts. For all this diversity, galaxies are far from arbitrary. Their properties obey tight low-scatter correlations, the scaling relations, the strongest single evidence that galaxies form a physically ordered family, governed by common dynamics. For disks, the central example is the Tully-Fisher relation, discovered in 1977. The total luminosity of a spiral rises steeply with its maximum rotation speed, roughly as the fourth power of that velocity. The rotation speed measures the depth of the galaxy's total gravitational well, dominated by dark matter, so the relation ties the visible light to the invisible mass. And it grows tighter still when luminosity is replaced by the combined mass of stars and gas. This baryonic Tully-Fisher relation holds as a single unbroken law across 5 decades of galaxy mass, from giant spirals down to the faintest gas-rich dwarfs, a stringent test any theory of galaxy formation must pass. Spheroids obey their own scaling laws. The Faber-Jackson relation, from 1976, links the luminosity of an elliptical to its velocity dispersion, the spread of random stellar speeds again, roughly as the fourth power. But this is only the edge-on view of a tighter, two-dimensional pattern, the fundamental plane. Elliptical galaxies occupy a remarkably thin sheet in the space of their size, their velocity dispersion, and their surface brightness. That the plane is tilted away from the simple prediction of the virial theorem reveals that the ratio of mass to light varies systematically along it, climbing with galaxy mass. A parallel law governs chemistry. The mass-metallicity relation, traced across tens of thousands of galaxies, shows that more massive galaxies are richer in heavy elements, because their deeper gravity holds onto the metals that supernova winds blow clean out of their smaller cousins. Two final relations knit morphology to the grand story of galaxy evolution. The first is the color bimodality. Sorted by color, galaxies split cleanly into a tight red sequence of old, quiescent, gas-poor spheroids and a looser blue cloud of young, star-forming disks with a sparsely populated green valley between. That the valley is so empty implies galaxies cross it quickly, their star formation abruptly quenched by some mix of gas exhaustion, feedback, and environment. The second is the M-sigma relation, among the most astonishing correlations in all of astronomy. The mass of the supermassive black hole at a galaxy's center is tightly tied to the velocity dispersion of the surrounding bulge, across more than 2 orders of magnitude. A black hole millions of times smaller than its host somehow keeps step with it, compelling evidence that the growth of black hole and galaxy are coupled, most likely through the energy the black hole pours back into its surroundings. Morphology, finally, is not fixed. A galaxy's form is sculpted by its encounters, and the modern cosmological view treats the Hubble sequence as a set of slowly evolving states rather than permanent types. When two comparable galaxies collide, their gravity flings out spectacular tidal tails and bridges of stars, as Alar and Jory-Toomer showed with their models in 1972, and a major merger of 2 gas-rich spirals drives gas to the center, ignites a colossal starburst, feeds the central black hole, and scrambles the ordered disks into a single pressure-supported elliptical. In the crowded environs of clusters, gentler forces act. The hot intracluster gas strips the cold gas from an infalling spiral, trailing it in the glowing tails of a jellyfish galaxy and slowly starving it into a lenticular. A galaxy's present shape is thus a palimpsest of its whole history, and to read its morphology is to read its past.